Welcome back to Honors Calculus. In this video, we're going to continue our discussion of continuity at a point by looking at how to evaluate limits. In the last video, we looked at the definition of a limit and we were able to prove that a limit works at a certain point. And while it's an important tool and an important definition, it is very cumbersome. So if I get my head out of the way, we can dive in and start looking at a couple of rules we can use to evaluate limits faster in good conditions. My first theorem tells me that the limit as x approaches c of x is equal to c, and the limit as x approaches c of some constant a is a. Things that seem fairly reasonable. And the proof here is so obvious that it's hard to say that anything is really happening. Let's let epsilon be a positive number and pick delta equal to epsilon. So if x satisfies 0 is less than the absolute value of x minus c is less than delta, which in this case is epsilon, well then, very clearly, absolute value of x minus c is less than epsilon. And that is f of x, and that is L. And less than and epsilon are two different symbols. So immediately, without any effort whatsoever, we have that the first statement, limit as x approaches c of x is equal to c, satisfies the epsilon delta definition of a limit. For the second statement, we're again going to let epsilon be greater than 0. We're going to pick delta equal epsilon, and we're going to assume that 0 is less than x minus c is less than epsilon. Then if we take the absolute value of f of x minus L for the second one, a minus a, you get 0, which is clearly less than epsilon because we defined epsilon to be greater than 0. And so once again, we have the definition of the limit without doing any work whatsoever. That's one of the easiest theorems to prove that I've ever come across. That theorem on its own is not all that valuable, but we can combine it with one other theorem. My one other theorem is that limits are linear. Let's pick a real number a. Let's also pick a real number c. Forgot to add that in. And let's let f and g be real valued functions whose limits are defined as x approaches c. Right? This theorem tells us that we can take a constant multiple out in front of the limit. The limit of a times f of x is a times the limit of f of x. We can also split limits up over addition. The limit as x approaches c of f of x plus g of x is the limit on f of x plus the limit on g of x. These two properties together are called linear. And whenever you have a linear operation like this, there are a lot of convenient tools that you can use. But we can't just state the theorem and go, we have to prove it. And in order to prove it, we actually need a name for the limit as x approaches c of f of x. Let's call it L. And let's let epsilon be greater than 0. And I also want to notice here the absolute value of a is greater than or equal to 0. So epsilon over the absolute value of a is greater than 0 if a is non-zero. Why is this useful? Well, the black magic that is mathematical proof. Somebody much smarter than me went through and came up with the most elegant way of approaching this. And so now I present it to you as people before have presented it to me. Once you see how it works, it makes sense. But looking at it the first time, you wonder, where did they come up with this epsilon over the absolute value of a? Well, they came up with it because it worked. Since the limit of x approaches c of f of x is equal to L, there must be some delta greater than 0 such that when 0 is less than the absolute value of x minus c is less than delta, we have that the absolute value of f of x minus L is less than some positive value, which we normally write as epsilon, but we could just as easily pick the positive value right here, that is epsilon over the absolute value of a. Now, we are looking for the limit as x approaches c of a times f of x, which means we want the absolute value of a times f of x. And the theorem claimed that this was going to come out to be a times the limit. So that's a times L. And we can factor out the absolute value of a. And giving us the absolute value of a times the absolute value of f of x minus L. But we just stated that the absolute value of f of x minus L is less than epsilon over a. So this is less than the absolute value of a times epsilon over the absolute value of a, which is equal to epsilon. I'm going to put a really small QED box here because that's only proving one statement, not the entire theorem. But that does give us that the limit as x approaches c of a times f of x is equal to a times L. You can take that constant factor out in front of a limit. I do have to put the caveat in here that this only works when a is non-zero. if a is 0, then instead we're going to evaluate this directly. The limit as x approaches c of a times f of x. If a is 0, you multiply 0 times anything, you get 0. And the limit of a constant is the value of that constant by the first theorem we proved. And of course, 0 is the same thing as 0 times anything, so we can multiply it times the limit as x approaches c of f of x. If we really want to, it doesn't do anything, but it makes it look like the theorem says it's supposed to look. So if a is not 0, we're good. If a is 0, we're also good. Now let's look at the second half. And for the second half, we're going to claim that since epsilon is greater than 0, epsilon over 2 is also greater than 0. Right? Same idea. 2 is a positive number. You divide two positive numbers, the result is positive. The positive numbers are closed under addition and under multiplication, and division is really addition in disguise. So dividing two positive numbers we know is going to give us a positive number. So we have epsilon over 2 as a positive number. All right. So by definition of a limit, there exists a delta 1 greater than 0 such that the absolute value of f of x minus L is less than epsilon over 2 whenever 0 is less than the absolute value of x minus c is less than delta 1. And there exists some other value, delta 2 greater than 0, such that the absolute value of g of x minus its limit, which we haven't written down yet, but we can call it something. Let's call it k. So g of x minus k in absolute value is also less than epsilon over 2 whenever 0 is less than absolute value of x minus c is less than delta 2. Now we want delta to be the minimum of delta 1 and delta 2, whichever one is smaller. Because if zero is less than the absolute value of x minus c is less than this new value delta, then it is also true that 0 is less than x minus c is less than delta 1, because delta 1 is less than or equal to delta, and 0 is less than x minus c is less than delta 2, because delta 2 is less than or equal to delta. I'm sorry, I said that backwards. Delta is smaller than delta 1. Delta is smaller than delta 2. So if absolute value of x minus c is smaller than delta, it is also smaller than both delta 1 and delta 2. So picking this value satisfies both of those, which means that we get both of these inequalities. All right. The idea we are looking for here, the claim is that the limit as x approaches c of f of x plus g of x is going to go to the limit of the sums, L plus k. I can rearrange this and get this as f of x minus L plus g of x minus k to get this looking closer to what we just had. And now I have the absolute value of the sum of two things. The triangle inequality says that this is going to be less than or equal to the sum of the absolute values. So we'll introduce the triangle inequality here to make this a little bit more manageable. And of course, we know that the absolute value of f of x minus L is less than epsilon over 2. And we know that the absolute value of g of x minus k is also less than epsilon over 2. And epsilon over 2 plus epsilon over 2 is epsilon. So we have the absolute value of f of x plus g of x minus L plus k is less than epsilon, which is the definition of limit as x approaches c of f of x plus g of x is equal to L plus k. And again, right here at the end, you see why we chose that strange setup of epsilon over 2. Because someone went through with ugly values and realized that if instead of using epsilon, we used epsilon over 2, then when we added everything together at the end, we'd get less than epsilon, which is what we really want. And it makes the proof look a little bit nicer. To the uninitiated, this is what makes mathematics look like a black art. To those of you who know what's going on, it makes a lot of sense. And one of the things that I want you to get out of this course is realizing that if you go to the end, you will realize why they chose what they did. And you'll also realize that this was not written exactly in the order that we wrote it down. Someone went through, wrote the whole thing out, realized they had a bunch of ugly values, and then did some creative editing going back, filling in and making everything work out in the end. But with that, we've gotten both properties of linearity. We can say that absolute value is a linear function, and we can go on, our absolute value, the limit is a linear function, and we can go on and use this property. So for example, I might want to look at the limit as x approaches 5 of 7x plus 3. By linearity, I can split this up into the limit as x approaches 5 of 7x plus the limit as x approaches 5 of 3. And also by linearity, I can split that first one up into 7 times the limit as x approaches 5 of x. And then this is still the limit as x approaches 5 of 3. Now, using the first theorem, limit as x approaches c of x is equal to c, limit as x approaches c of a is equal to a, we get 7 times 5 plus 3. 7 times 5 is 35. 35 plus 3 is 38. And we see that when we have a well-behaved function, and there are no functions better behaved than linear functions, when we have a well-behaved function, the limit is just telling us to evaluate the function. Up next, we want to look at situations where functions can start to become a little bit more complicated. And we will do that by looking at an idea called the product rule, which says that the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. From the perspective of a mathematician, this theorem really starts to get into how flexible limits are. Limits can basically allow you to ignore everything, and they ignore anything that you throw at them. They're really fantastic like that. Although to get this much power, the proof is kind of exotic. Let's define that the limit as x approaches c of f of x is equal to L, and that the limit as x approaches c of g of x is equal to k, same definitions that we've looked at before. And now I'm going to do something that looks really strange. Once again, these are the kinds of things where someone much smarter than I figured out how this is supposed to work, and I've studied it and I understand that it does work. I have no idea how someone came up with it in the first place. Those of you who are moving onward to a course in, say, real analysis, learning how to structure these things is important in that class. For right now, we are looking at understanding that it does work. Because these are not actually the functions I really want to look at. Instead, I want to look at the limit as x approaches 0 of f of x minus L, and the limit as x approaches 0 of g of x minus k, which, using the property of linearity, this is going to be the limit as x approaches, not 0, the limit as x approaches c of f of x, the limit as x approaches c of g of x. All right, so that'll be L minus L, which is 0, and that'll be k minus k, which is 0. I got ahead of myself and I really wanted to get those zeros in there. Now we will use the definition of a limit. Let's let epsilon be greater than 0. And this time we'll note that the square root of epsilon must also be greater than 0 when epsilon is greater than 0, because square root is a non-negative function. Square root of anything is either greater than or equal to 0. And if the thing you're square rooting is positive, then the square root comes out positive. If the thing you're square rooting is 0, the square root comes out 0. If the thing you're square rooting is negative, then the square root blows up and gives you a complex number. And we're not talking about complex numbers in this course. Same sort of structure that we've looked at before, only this time we're using square root of x, because black magic and someone figured out that that works nicely in the end. So we find a delta 1 that works for the limit on f of x minus L. We find a delta 2 that works on the limit of g of x minus k. And we pick delta to be the smaller of those things. And now, no, we don't want to look at f times g by itself. We're going to look at the product of these functions. The product of f of x minus L times g of x minus k, we're going to claim has a limit of 0, which should make sense. The limit on f of x minus L is 0, the limit on g of x minus k is 0, although we haven't proven that yet. So I'm going to work through this and split. Notice that subtracting 0 doesn't do anything. This is just f of x minus L times g of x minus k. And the absolute value of a product is the same thing as the product of the absolute value. So we have absolute value of x minus L times absolute value of g of x minus k, which we know is less than the square root of epsilon times the square root of epsilon, which is equal to epsilon. So now we know that the limit as x approaches c of f of x minus L times g of x minus k is equal to 0. So the limit as x approaches c of f of x minus L times g of x minus k is equal to 0. But I can multiply that stuff in there out. This is where the proof gets really fun. If I multiply all of that out, I get that we're looking at the limit as x goes to c of f of x times g of x minus k times f of x minus L times g of x plus k times L. And I know that that has to be equal to 0. And then I can use the linearity of limit to split this up. Right? This is the limit as x goes to c of f of x times g of x minus k times the limit as x goes to c of f of x minus L times the limit as x goes to c of g of x plus, well, it would be the limit as x goes to c of k times L, but k and L are both constants, so I'll just leave those as k times L. All right. So we have this limit as x goes to c of f of x, g of x, which is exactly what we are trying to figure out. We have this k times limit as x goes to c of f of x, which is L. We have this minus L times limit as x goes to c of g of x, which is k. Minus KL and plus KL cancel each other out, leaving us with minus LK, which is the same thing as minus KL. Or I guess I should leave that as LK. And finally, I can add that LK to both sides of the equation to get that the limit as x goes to c of f of x times g of x is equal to LK, the limit on f times the limit on g. That's a fun proof. It goes really into some esoteric places. Again, my expectation is not that you can figure out how someone came up with this proof. My expectation is, having seen it, it should make sense. You can see how they went through step by step by step. Right. There are two very simple corollaries to the product rule. Remember, a corollary is a proof that, or a theorem whose proof is very straightforward once you have another theorem proven. The corollaries are the quotient rule, the limit as x goes to c of f of x over g of x is the limit as x goes to c of f of x over the limit as x goes to c of g of x. And you can prove this one pretty quickly by defining h of x equals 1 over g of x and realizing that this is just a product. And then I have a corollary, the limit as x goes to c of f of x raised to the n power is the limit as x goes to c of f of x raised to the n power. And you can prove this one pretty quickly by applying the product rule n times, or I guess n minus 1 times. So with that, we now have the tools to deal with limits involving multiplication, division, and powers. So if we take a polynomial or a rational, we should be able to evaluate the limit no problem. For example, if I want the limit as x goes to 2 of x squared plus 3x plus 5, well, it's going to be the limit as x goes to 2 of x squared plus 3 times the limit as x goes to 2 of x plus the limit as x goes to 2 of 5, right? Use linearity, then use the power rule that we just talked about. And the limit as x goes to 2 of x is 2, so we have 2 squared plus 3 times 2 plus 5. Exactly what you would get if you just evaluated the function at the point. When a function is well behaved at a particular point, evaluating its limit is just evaluating the function. When the function is not well behaved at a point, that's when limits start to get interesting. All right, so let's take a look at the limit as x goes to 4 of x plus 3 over x squared minus 5x minus 6. And here you will notice, again, that this function is well behaved at the point x equals 4. So we should be able to get everything to work out no problem. The limit as x goes to 4 of x plus 3 over the limit as x goes to 4 of x squared minus 5x minus 6. All right, I'm not going to write out using the linearity and using the power rule like we had in the last couple of examples. Let's just plug in x equals 4. Right, the limit as x goes to 4 of x is 4. So we have 4 plus 3, which is 7, over 4 squared, which is 16, minus 5 times 4, which is 20, minus 6. 16 minus 20 minus 6 is negative 10. Right? Leaving negatives in the denominator of a fraction is considered a bad thing, so we'll bring that out in front and call it negative 7/10. One more theorem here is the substitution rule. Let's let f and g be functions so that f of x and g of x agree with each other everywhere except at x equals c. Then the limit on f of x is equal to the limit on g of x as x approaches c. So the way that this theorem is going to be used in practice is we're going to have one function whose limit we can find easily and one function whose limit we could not find easily. Let's pick g of x and say that the limit as x goes to c of g of x is equal to L. That's not the k we've been using before, but it's going to be the same limit for f and g, so we might as well just call them all L. And let's let epsilon be bigger than 0. And there exists a delta greater than 0 such that the absolute value of g of x minus L is less than epsilon when 0 is less than the absolute value of x minus c is less than delta. The important thing to note here is that when 0 is less than the absolute value of x minus c is less than delta, x is not equal to c, which means that f of x is equal to g of x. And since f of x is not equal to g of x, we can substitute and say that instead of g of x minus L less than epsilon, we want that f of x minus L is less than epsilon. That's all it takes. This is where limits come to shine. Consider the limit as x approaches 1 of x minus 1 over x squared plus 2x minus 3. If we tried just substituting in, we would get 1 minus 1 over 1 plus 2 minus 3, which is 0 over 0. Right? 0 over 0 is called indeterminate. 0 divided by anything is 0. Anything divided by 0 is 1. I'm sorry, anything divided by 0 is undefined. And those two rules say that this is both 0 and undefined, which makes no sense. So we call it an indeterminate form. But note that x minus 1 over x squared plus 2x minus 3, that denominator factors into x minus 1 times x plus 3. And now I can cancel out the x minus 1s, leaving me with 1 over x plus 3. And 1 over x plus 3 is equivalent to what we had everywhere except when x equals 1. And 1 over x plus 3 is something we can take the limit of. We get out 1/4. So by using this rule, we can reduce the fraction. We can evaluate a function that is actually defined at the point, and that will give us the limit of the function that we could not define at the point because it wasn't defined. I would like you to try a very similar looking problem. I'd like you to consider the limit as x approaches 5 of x minus 5 over x squared minus 25. Using the theorems that we've just been talking about, evaluate this limit. Take a few minutes to write that one out, and I'll see you in the next video.